Welcome. I'm going to maybe do a quick introduction. The meat of this presentation, I want to thank Bob for taking the initiative and putting this together and getting Lewis and I to help along. And it speaks to perhaps the collaboration that we see here of an opportunity on the lower Jordan River. So that's the portion below the bifurcation of the surplus canal. There's a lot of opportunity and need in that reach. And maybe the setup of this conversation is many of you may know that we're under a total maximum daily load associated with dissolved oxygen episodes where the habitat is impaired relative to oxygen depletion. And as we're getting to understand that system, it presents some opportunities for restoring natural function. Maybe with that, I'll let Bob take it. And with some, when you get intelligent people with a lot of great experience together, like Bob and some others here, we have some great opportunities.
All right. So I'm here to talk mostly about kind of the design components that are going into the 17th South project. There's a lot of partnerships that are going to happen with this. There's going to be a lot of collaboration. I'm just going to talk about the function of the river currently versus what we'd like to see at this location. So as all of you, I'm sure, know, the Jordan River is in fact impaired. The natural function of the river has ceased to be there for a number of years. And I don't really want to have a lot of text on the screen. I want this mostly to be a visual presentation. So this is a picture of the reach we're talking about. So we're looking at the Jordan River. This particular spot is where we started our survey for this stretch, and you're looking to the south. So 17 South would be the road you're looking at back by the pine trees, and we surveyed downstream of here. The river at this location is, well, I guess the picture kind of tells the story. You've got a lot of some native plants, a lot of non-native plants. The river itself doesn't really have a functional floodplain. It's mostly just a channel that's been dredged out over the years. So the form is really not natural. I'm not here to talk necessarily about form by itself. I'm here to talk about the river as a whole. This river is, on paper, the same stream type. This one is obviously not the Jordan River, but they don't really look the same. So kind of what I'm here to talk about is why there's a difference, what the differences are, and what we can do to restore the Jordan River back to more of a functional system like this. So the first thing I'd say about this one, the width to depth ratio on this stream compared to the Jordan River is completely different. Even though your bankful discharge, your 100-year flows are within 50 CFS of each other, this one's a much smaller stream. The width of this one's about 25 feet. The Jordan River at this location is 60 feet. So that's one difference. Second difference, this one's obviously got a gravel bed stream. You're looking at kind of a glide section moving into a riffle section. Substrate's completely different, even though you have basically the same hydraulics working on this. They've been altered in this version, so our job here is to figure out how we can alter that back. The sediment transport capacity of this stream is completely different than the Jordan River. The riparian vegetation is totally different, and you can actually see this one has an extensive connected floodplain. So if we can restore some of those functions to the Jordan River, I guess the question is, can we restore the Jordan River to a functional state? The one thing we cannot change in the Jordan River at 17th South, this picture's up near Mildy and Big Cottonwood Canyon. We can't change the water quality of the inflow. So in this location, we've got pristine water coming at us. Here, not so much. So, turn it over to Lewis for a minute.
Okay. So, right. And then our program is responsible for the management of the land along the river, along most of the river corridor from about 21st South to 23rd North, and I think that it's important for us to take a quick step back and before we jump into a significant river channel reconstruction project like we're proposing, to revisit the goals that govern our program's management of the parkway and ask ourselves, is it consistent? Is this kind of a river project consistent with our goals for the parkway? And our goals for the parkway primarily are the same as many of those that are in the blueprint Jordan River. And as I had mentioned earlier this morning in the panel, those goals primarily are restoring native plant communities and ecosystems to their fullest possible richness, diversity, and health along the river corridor. We're also very interested in bolstering river-adjacent neighborhoods and promoting the river as a natural asset. And then we're also looking for opportunities wherever we can to improve our opportunities for recreational enjoyment of the river corridor and for education and interpretive opportunities. And so, here we have an opportunity perhaps to restore the river channel along the river to improve and protect water quality, we hope, to enhance hydrological function, but also hopefully to support all these similar goals related to vegetation, wildlife, habitat, interpretive and education information, possibly even recreation. So I guess, in stepping back, reviewing that, and then assessing, I think that yes, absolutely, the answer is this type of project is fully consistent with our land management goals for the parkway. I'll turn it back over to Bob for a minute.
Okay, so the route we've decided to go for this, I think the reason why Tom and Louis want to work with me is I specialize in natural channel design. So the supposition behind natural channel design is that nature has provided the best blueprint to make a functional stream. So if you can mimic what nature does with streams, you can ideally create a stream that functions. So the first thing you do is you have to figure out what your stream is doing. So after going out there and surveying the stream, cross sections, longitudinal profile, pebble counts, the whole 9 yards, we then plug that into a number of models. We do approximately 23 different worksheets to get to this one to figure out what's going on with the river. What's going on here, if you can see the boxes that are checked here, this model indicates aggradation of the river, and this model down here indicates the same thing. So we're actually using 3 different models to try to do the sediment modeling analysis, figure out, okay, what's going on with the river in its current state. And the reason why we do 3 different models, we're looking for convergent lines of evidence, because sediment modeling historically has not really been the most reliable predictor of what's happening with rivers. We do tend to use some of the better models. I use FlowSed, PowerSed. We also use critical shear. We use, I guess the hydraulic analysis. But we come to a number of different conclusions, and in this case, they all pointed to the same thing. So another case study of where we've seen something like this happen, Salt Lake County, I'm not going to pick on anybody else's projects, just our own. We have a stretch of stream on Rose Creek at approximately 0.21 miles above the confluence with the Jordan River. And at one point, we had what's called an E-type stream. An E-type stream is a really narrow stream that's got kind of a low width-to-depth ratio. So the width of the stream compared to the depth of the stream at a bank full flow gives you a low number. So in this case, the width-to-depth ratio, as I have it right here, was 3.82. The slope of this section was 0.005, so it's a very flat section. Width of bank full was 15 feet, cross-sectional area 38 feet. And then down here, the sediment that was found in this, 22 millimeters, and a maximum sediment particle of 126 millimeters. And then we put in a box culvert so we could put in a gauge there. When we put in the box culvert, we decided we were going to oversize the channel so we'd have plenty of room to move the water through. When you add plenty of room to move the water through, you change the river's ability to function. This is the new cross-section of that river. And as you see over here, the numbers that can't change didn't, but everything that could change did. So the slope, that didn't change. Width of the bank full, we did change that. Cross-sectional area, we did change that. Width to depth ratio, that ended up changing. And then we incised the channel. And then if we look down here at the sediment, that changed by an order of magnitude. So the river's ability to move sediment through this section, exactly the same location, massively changed. And it's only a 20-foot long section. And what's really interesting about that, after this channel right here was built, the river rebuilt this one on top of it. So with the first storm, the river deposited 2 feet of sediment, and then almost this exact geometry was rebuilt. So what that tells us is the river knows what it wants, and it's going to tell us every time. So this has been documented by people for a long, long time. This is not a new observation, and if we follow the rules that have been kind of figured out in the past, we could learn a lot. So the implications of this, there are certain streams that belong in certain places and other streams that don't belong there. So if we tried to build one of these threshold channels with massive particles down here, it's not the best fit. Try to build a sinuous stream that exists down here, up here, again, not the best fit. So natural channel design, we're trying to put the right stream in the right place. So what we do, We start by a survey. We go out there, we do the longitudinal profile, fixed cross sections, we monitor it. We use reference reach survey data to compare and to try to determine how far away from our reference reach condition that impaired reach really is. We analyze all the boundary characteristics, all the stuff that we can't change, modeling, conceptual design. Then we go through the permitting process, come up with a final design, then comes construction, and then monitor and report. And I think a lot of projects, this is seen as kind of a bad thing, but it's an opportunity. You're never going to get good at this kind of work unless you do that. Monitoring and reporting is absolutely critical. So in this project, that's going to be one of the kind of the cornerstones.
Okay. So Bob, the reason we actually, Tom and I like to work with you, it helps that you're good at river math, but we think that they might let us out of the office every once in a while if we work on a project with Bob. So I wanted to talk for a minute about the opportunity that this area represents. Why 17th South? This particular site, I should say Salt Lake City's section of the Jordan River and the Jordan River Parkway is probably far more constrained by development, especially by residential development, than I think any other segment of the river. And so within Salt Lake City, when we're looking at opportunities for restoration projects, the size of the property, the larger the property, potentially the more restoration we're able to do there. And I think that our program has collaborated with the county and city public utilities on projects that are very small, half-acre in size or even smaller, but certainly where we have larger opportunity, larger acreage, we can do a bigger project of this sort. And this particular open space area, just north of 17th South, is the largest one that we have on the Parkway, between about 2600 South and 18th North, so a section of about 9 river miles. This particular site is about 16 acres in size, and so that represents a pretty excellent opportunity. Another thing to take into consideration is what are the pre-existing uses, what will change if we do this, and this particular site, the slide here is kind of looking across the open area where the proposed relocation of the river channel would go. And currently there are virtually no pre-existing uses of the site. There is a art installation that would not be disturbed by this project, and the Jordan River Parkway Trail traverses along the east side of the site. Otherwise, really this is a great site for us to engage our community groups in picking up trash. But I think that there's a lot to be gained by improving this site, adding floodplain, and then all the things that go along with it. So just looking at some boundary conditions and taking kind of a deeper look at what is here. There is a USGS gauge at 17th South, right down here, that we know we can't disturb. There's also a stormwater drain on the site that we can't disturb. That's right up here. And then there's an art installation right near the center of the site that we also can't disturb. We know that flood control needs to remain, they need to still be able to remove sediment from the river. And we know that the channel must still be able to handle up to a 100-year flood event. And then we have some other, and I should also add the channel needs to remain navigable. We're also very interested in this project potentially creating additional wetland habitat or maybe a community fishery. And there are also funding constraints when we're looking at a project like this. Hauling material off-site, and especially hauling it a long distance, quickly becomes cost prohibitive. And so if we can look at a design that allows us to minimize the amount of material hauled off-site, that certainly helps. It's also, and I think Bob will probably get into this, but some other site constraints include that a short distance upstream of this, the surplus canal takes off and runs towards the Salt Lake. And that canal ends up diverting a lot of the native substrate and also takes the majority of the river's flow, especially during high flow events. So there's a lot of interesting limitations and conditions here. And I think I need to let Bob talk about how those challenges can be addressed and accommodated.
Okay. So this is the results of our survey. We have to figure out exactly what we have. So this first cross section that you're looking at, this is a riffle cross section. And one thing I want to point out on this riffle cross section, this line right here does not represent water surface, nor does this one. This line right here represents a bank full flow, or roughly a 1.2 year return interval flow. This one right here represents the top of the inner berm or the low flow channel. So water surface at the time we surveyed was actually located here. This line up here represents your flood prone area, or in this case that represented almost a 500-year event. So to get water outside of the channel, you need close to a 500-year event. So what a lot of people call a floodplain, this surface that's up beyond here, it's not a floodplain. That's a terrace. So what we need to build right here obviously needs to incorporate flooding. So this line right here is more akin to the elevation. The other thing I wanted to point out, this channel right here would represent a trapezoid if not for this triangle right here. When we were surveying that, that was almost hip deep sludge. I mean, it was really fine in its gradation. And if you've ever been in a riffle before and you've got silt accumulating there, you've got big problems. This river is not functioning. This is a pool. So this one had a deeper outside bend than it did on the inside bend, and that more or less is what you ought to see on a pool, but the lines represent all the same stuff. So this one right here represents your inner berm, or the top of your low flow channel surface. This is your bank full surface, and this right here is your flood prone area, again representing almost a 500-year event. So even in this section right here, and this one has actually had restoration done on it, so this outside bend, there's riprap there, there have been plantings installed there, but we still have this surface right here that is significantly above our bank's full surface, so it does not function as a floodplain. This is our longitudinal profile. Just to sum this one up, we've got a lot of pools, not a lot of riffles, and our glides are way too long. So if we compare this to a reference reach, our numbers are pretty far out of whack. So this reference reach is a picture. This on paper is what the big cottonwood reach that I showed you at the beginning of this presentation represents. So our bank full flow, they're pretty close, not significantly different. Our 100-year flow, there's a little bit of a difference there. In the Jordan River, because, as Lewis said, most of the flow is taken down the surplus canal, our 100-year flow in this design scenario is only 500 CFS. So it's much smaller than it would normally be without that surplus canal diversion. Our width to depth ratio is a little over twice of what it should be. Our channel is highly incised. Instead of having a bank full surface that is the floodplain, our bank full surface is almost half the floodplain. So that floodplain is elevated way too high. Radius of curvature isn't too bad. Our linear wavelength is way too long, and our sinuosity, it doesn't even compare. Oh, I actually have these switched. My apologies. This is supposed to be 1.0, not supposed to be 1.6. So, oh, no, I have those right. Sinuosity right there is 1.0. So basically we have no functional sinuosity in the Jordan River channel. Even though it's on a bend, there really isn't a functional sinuosity there. So the next thing we had to do is try to come up with a channel that could actually solve the problems that we just described. So what we're going to build is a channel that is much narrower across the top and the bottom, has much steeper sides, and has a much wider floodplain. Now I apologize for the vertical exaggeration on the scale. I just use relative elevations on this side. It doesn't really matter what the elevations are. It just shows that that's how high we're going to build. So right here, if this is our zero elevation, we're going to build a low flow channel that's 4 feet deep in a riffle. So that's all this is trying to show us. Our floodplain right here is going to be well over 100 feet across. So instead of having no floodplain, we're building a floodplain. We're also going to build in a low terrace, because one of the things that Lewis told me right in the beginning is he wanted to have more native cottonwood groves. He wanted to have more native vegetation where you could actually have people come to the park and enjoy the space. If you put those things right down here where we have a 200 CFS flow topping the banks, the cottonwoods are going to be inundated way too often. So we really needed to build a low terrace. So we're building a 4-stage channel. The lowest stage is the base flow stage. Above that, we're going to have the floodplain. Above that, we have the low terrace. And above that, we'll have a high terrace. And so the challenge here was making sure that our bank full stage really was the floodplain, meaning the 1.2-year return interval flow would escape that low flow channel at that point, which was 200 CFS. So that worked out. We had to keep the 500-year event, the 100-year event or 500 CFS contained in this high terrace. Again, it all worked out. Took a little bit of playing, but we were able to do it. Next, we modeled the sediment with the proposed channel design. Again, 23 worksheets later, we got to a stable channel here and a stable channel here. The number I had to manipulate was up here in the largest particle present. Because we've cut off our native substrate from running down this channel with the structure that's at the surplus canal, we're actually going to have to treat this like a threshold channel. We have to put in particles that won't move because there is no recruitment of gravels. I would normally build an alluvial channel at this point because you would have recruitment of gravels, so you could resupply with every flooding event, but here we don't have that opportunity. So what we have to do is make sure that our D50 particle size is going to be 35 millimeters. And that should make sure that it stays in place according to everything we put together with channel hydraulics. And so this is what it looks like in plan view. So what we've done here is we've taken the normal channel which flows this direction. So 17 south is right here. The channel flows through here, moves around this bend, and this is the bend that's been restored right here, comes around here, and then flows further north. So what we've done is we've kind of put a cutoff structure right here. We're going to route the channel around here. The peace tree structure is right here, so we're kind of using that as a focal point of the bend. We're going to do a compound pool structure here and then follow the radius of curvature that we got from our reference reach through the rest of the bend. We're not going to use any riprap to armor these. The structures that we've designed on the outside of the bends are called toe wood structures. We've tried these on other parts of the Jordan River and they've worked extremely well. The best part about these, we're actually finishing a project right now about 51st South, and we got approximately 400 trees this year. Every single one of them was free. So it's really nice when you can do a project where your revetment material comes at no cost. The other thing we're trying to add into this design, we really wanted to have some community fisheries / wetland treatment plant facilities. So we're actually going to divert some of the water at this diversion structure and we're going to put that into these ponds. Now what we've drawn up right here are 2 ponds that equal 1 acre in size. Now I know there's kind of a rule of thumb where you should always have a pond at 1 acre and you should always have it at least 16 feet deep, and there's a lot of rules that people tend to follow. But these ponds, if we follow this design, they're going to have about 4 CFS coming into them at low water. So we're going to have a tremendous amount of recharge coming into these. They're not going to stagnate. So the last question we have to answer is, ponds tend to fill up with sediment, and especially in this section of the Jordan River, we are overloaded with silt. So if you put a structure in that we're calling a sediment sluice, we can actually alleviate that. It will require some maintenance in the form of somebody out there actually turning the sluice, or it's a screw gate that you have to shut during high or low flows and open it up during high flows to flush sediment through. But if we're willing to do that, we can actually build a structure that's going to keep the sediment out of these ponds, keep it moving down the channel, and then to accommodate flood control, because we do have this constant sediment moving down the channel and it is not the native gravels. We're going to build, I can't actually zoom out far enough on this because it's just a picture of what the design is. We're going to build a flood control specific hardened pond further up this channel, and during years of high flow when sediment does tend to accumulate, that'll be a designated spot for flood control to come in, pull that sediment out, and there's going to be a staging area for them, so it's not going to be a continuous dredging project throughout the entire channel. It's going to be a specific location. But again, we've shown that there's enough velocity to move the sediment through this that we have a stable channel, neither aggrading nor degrading. So, Tom, let's see.
Just got the 1-minute cue. I think bringing this home back to the water quality issue, we see that part of the solutions from a water quality perspective on the Jordan River, certainly we have the urban stormwater runoff and the BMPs need to be applied, but we believe that part of the solution is restoring the natural function, as Bob has mentioned. And I think one of the elements is that gets us into the river in terms of that design. And so we see an opportunity there. You've got a number of the Jordan River, the Blueprint Jordan River, we got flood insurance studies. We have a number of interests that come together in this synergy, you know, with Lewis from our parks and open space side of things, the recreational, the habitat side. My department, which is the flood control and the water quality side from the city, in partnership with the county, we really bring together a range of needs with a number of opportunities with a singular solution, kind of an integrated watershed management solution perspective. Back to the water quality, I don't know if I expressed this well enough. As that sediment deposits and you have methane generation and you have high flows come and then stir that up, we believe that's at least one of the mechanisms is causing the dissolved oxygen sink. So by using the channel section that that Bob has described, now we can force the sediment to not have that DO event, right? But in the meantime, we end up with a habitat. We end up with a natural stream function. We end up with really a natural system engineered back in our local community. So, got a little time, Sam, for questions. Next steps, I think we've talked about this. This becomes a pilot project for us. So there's the permitting, the funding, and then we see it being part of a master plan, really in partnership, not just with our entities, but with the state and other stakeholders. And then there's a lot of opportunity for the whole Lower Jordan River. Can I take one question? Ty. The question is, will our 17 South storm drain, we have a pump station. Salt Lake City has a number of pump stations and outfalls. I bring up this slide here. The project that Bob's talking about is doing the geometry here. I bring this one up because we see another solution that we haven't illustrated here is when we have an outfall, rather than just being a treatment wetlands or whatnot, there's another function that happens. If we have a pipe that goes in, it's going to stir everything up. If we can create a wetland where now you have 100 feet of it gradually coming in and not stirring up that river or lake, that we see that being another engineered natural stream function. So to answer your question, we see, not in this project, but other projects, taking our outfalls and doing them in a better way.